Friends, welcome to the tutorial series on network analysis made simple. We know that whenever the circuits are switched either by change in supply source or by change in circuit elements, there is a transitional period during which branch currents and voltages across the circuit elements change from one former value to the new values. This transition period is called as transients. If you remember, during our previous tutorials titled Classical Approach to Transient Analysis and Step Response of RL and RC Circuits, we defined the transients as a state which lie in between the two steady states. In these previous tutorials, when the circuits are switched, we obtained the behavior of circuit elements at t is equal to 0 plus and at t is equal to infinity using classical approach. During this tutorial titled Evaluation of Initial and Final Conditions in RL, RC and RLC Circuits, first we shall find the initial and final conditions of resistance, inductance and capacitance taking individual circuit elements and then go to different circuits. Friends, to keep you in comfortable zone, to understand the concepts involved, I wish to take you through hassle-free path without involving deeper mathematical jugglery. Hope you will be happy to go through this interesting tutorial. Friends, first let us consider the pure resistance circuit element connected across a DC source as shown in figure. When the switch K is closed at t is equal to 0, you find that the input to voltage takes the form of a step input as shown. Similarly, we find that a current in the circuit also will vary in the same manner. If we observe the variation of current at t is equal to 0, we find that I of 0 is equal to V by R amperes. Similarly, at t is equal to infinity also, I of infinity is equal to V by R amperes. How do we substantiate this? Let us use a very simple mathematical identity. I of t is equal to I of infinity plus into bracket I of 0 minus I of infinity into e to the power of minus t by tau. By substituting the values of currents at t is equal to 0 and at t is equal to infinity, we get I of t is equal to V by R amperes. It means it confirms that the current in the resistance follow Ohm's law. Next, consider an inductance circuit element. We know that every inductance will have some amount of resistance, however small it may be. So, inductance can be considered to be a series combination of a resistance and a pure inductance as shown in figure. We know that VL is equal to L into di by dt or L is equal to VL divided by di by dt means the inductance will oppose the change in current. Friends, when the inductance circuit element is switched across a DC source at t is equal to 0, the variation of current I of t takes the form of an exponentially increasing curve as shown in figure. By observing the graph, we find that I of 0 is equal to 0 and I of infinity is equal to V by R amperes. Then, using the same mathematical identity and substituting the values, we find that I of t is equal to V by R plus into bracket 0 minus V by R into e to the power of minus t by tau, which gives us V by R into bracket 1 minus e to the power of minus t by tau amperes. If we find the voltage across the inductance, we find that VL is equal to V minus VR, and by substituting the values of I, we find that VL is equal to V into e to the power of minus t by tau, where tau is called as LR time constant and tau is equal to L by R. By drawing the graph of both IL and VL, we get the graph as shown in figure, and we find that at t is equal to 0, IL of 0 is 0 and VL of 0 is V. It means a zero current and a finite voltage imply open circuit, and hence at t is equal to 0 plus L is open. Similarly, if we observe at t is equal to infinity, IL of infinity is equal to V by R amperes and VL of infinity is 0. So, a finite current and a zero voltage imply short circuit, and hence at t is equal to infinity, L is short. Using these initial and final values, we can draw the equivalent circuit of the given circuit at t is equal to 0 plus. So, you see that at t is equal to 0 plus, switch K is closed and L is open. So, I of 0 plus is equal to 0. Similarly, at t is equal to infinity, switch K is closed, L is short, and hence I of infinity is equal to V by R amperes. If we draw the equivalent circuit at t is equal to 0 minus, you see that at t is equal to 0 minus, the switch K is open. Note that. And inductance will behave as though it is at t is equal to infinity, because the switch might have been open for infinite time before closing. So, I of 0 minus is equal to 0. You see that at t is equal to 0 minus, I of 0 minus is equal to 0, and at t is equal to 0 plus, I of 0 plus is equal to 0. This will confirm that the inductance circuit element will oppose the change in current. Friends, let us next consider the capacitance circuit element. Here also, capacitance can be considered to be connected in series with its resistance as shown in figure. We know that current through the capacitance IC is equal to C into dV by dt, and C is equal to IC divided by dV by dt. This indicates that the capacitance opposes the change in voltage. Now, when the capacitance circuit is switched across DC voltage at time t is equal to 0, the input voltage takes the form of a step input as shown. When the switch K is closed at t is equal to 0, of course the voltage V is applied to the circuit, but we have to find out whether the capacitor is charged or not before switching. For that, consider the circuit at t is equal to 0 minus. At t is equal to 0 minus, K is open, and you see that the two terminals of the source are not connected to the capacitor at all. So, capacitor is not charged, and hence Vc0 minus is equal to 0. We know that the capacitance opposes the change in voltage, hence Vc0 plus is equal to 0. So, the entire voltage V appears across R, and hence I of 0 is equal to V by R amperes as shown. Later, the capacitance goes on charging and current through the circuit exponentially decreases and finally reaches 0. So, I of infinity is equal to 0. By substituting these values in the mathematical identity, I of t is equal to I of infinity plus into bracket I of 0 minus I of infinity into e to the power of minus t by tau, we get I of t is equal to phi by r into e to the power of minus t by tau, where tau is equal to RC and it is the time constant, as you know. To find the voltage across C, we know that Vc is equal to V minus Vr and Vr is equal to I into R, and by substituting the value of I, we get Vc is equal to V into bracket 1 minus e to the power of minus t by tau. By drawing both the graphs of Vc and Ic, we get the graphs as shown in figure. You see that from the graph at t is equal to 0, IC is equal to V by R amperes and Vc is equal to 0. It means a finite current and a zero voltage across the element imply short circuit, hence at t is equal to 0 plus C is short. Similarly, at t is equal to infinity, IC is equal to 0 and Vc is equal to V. So, a finite voltage and a zero current imply open circuit, and hence at t is equal to infinity, C behaves as open circuit. If the initial voltage Vc0 is present across the capacitor before closing, the capacitor will behave as a voltage source of Vc0 as shown. So, by incorporating these aspects, the equivalent circuit at t is equal to 0 plus can be drawn as shown in figure. We find that at t is equal to 0 plus, K is closed, C is short and Vc0 plus is equal to 0. Similarly, at t is equal to infinity, K is closed, C is open, note that, and Vc infinity is equal to phi. But at t is equal to 0 minus, K is open, you note that, and it can be considered to be open for infinite time before closing. Hence, the capacitance will behave as though the time t is equal to infinity. Hence, C is open and Vc0 minus is equal to 0. So, we find that at t is equal to 0 minus, Vc0 minus is equal to 0 and at t is equal to 0 plus, Vc0 plus also is equal to 0. So, it confirms that the capacitance opposes the change in voltage as we saw earlier. Friends, let me summarize the procedure for evaluating the initial and final conditions of the given network. Friends, you may please note that there is no unique procedure that must be followed in solving for initial and final conditions. Let me tell you an interesting fact. The renowned author Van Valkenburg in his text has expressed, quote, "It is a game of chess in that the strategy chosen depend on the particular problem being considered," unquote. However, friends, one need not be panic. Let us find the way. While solving for the initial conditions, when certain circuit is switched, say at t is equal to 0, if the initial conditions, that is the voltage across the capacitor and the current through the inductance, are given in the problem statement, that is fine, we can use them. Otherwise, we have to find them. The first point we should remember is about the resistance circuit element. All resistors and the sources are left as they are. Next, very important point is to keep track of the switch position. I mean, we should see whether the switch is open or closed at the instant of time under consideration. After drawing the equivalent circuit, we have to use the electrical circuit domain knowledge to find the required parameters. First, let us see how to obtain the initial conditions when certain circuit is switched at t is equal to 0. While drawing the equivalent circuit at t is equal to 0 plus, replace all the inductors by open circuit if there is no initial current through it. If there is initial current, say I0 is present before the switch is closed, then replace it by a current source of I0 amperes. Replace all the capacitors by short circuit if there is no initial voltage across it, or replace by the source of Vc0 with relevant polarity if there is a voltage across it present before switching. You may note these aspects. While drawing the equivalent circuit at t is equal to 0 minus, note that the circuit elements behave as though they are at t is equal to infinity because the switch will be in the respective position from t is equal to 0 minus to t is equal to infinity. So, replace all the inductors by short circuit if there is no initial current through it, or replace all the inductors by the current source, say IL naught, if there is initial current through the inductance. Similarly, replace all the capacitors by open circuit if there is no initial voltage across it, or replace the capacitances by a voltage source of say V naught if there is an initial voltage present across it before closing the switch. In all the cases, remember to keep the resistances and the sources as they are. Friends, To emphasize the concepts we have learnt, let us solve few examples. First, let us take an example to find I of 0 plus, di by dt 0 plus and d squared I by dt square 0 plus in the circuit shown in figure. The switch K is closed at t is equal to 0. Note that Vc0 is equal to 0 is given in the problem statement itself, but we don't know IL0 minus, hence we have to find it. So, first let us draw the equivalent circuit at t is equal to 0 minus as shown in figure. We see that at t is equal to 0 minus, the switch K is open and it could have been in open position for a long time or for an infinite time. So, at t is equal to 0 minus, circuit elements will behave as though t is equal to infinity. Hence, at t is equal to 0 minus, L is short and C is open. If we observe this equivalent circuit, we find that I of 0 minus is equal to 0 and Vc0 minus is equal to 0. So, I of 0 plus also is equal to 0 and Vc0 plus also is equal to 0 because inductance opposes to change in current and the capacitance opposes to the change in voltage. So, we have got one answer I0 plus is equal to 0. Friends, you will get the same answer even if you draw the equivalent circuit at t is equal to 0 plus, you can verify it. Now, to obtain di by dt 0 plus, let us use the system equation 1, which is R into I plus L into di by dt plus 1 upon C into integration I dt is equal to V. This is a general equation which holds good for all time t, so you should also hold good for time t is equal to 0 plus. Hence, by adding t is equal to 0 plus in all the terms, we get equation 2. But we know 1 upon C into integration I of 0 plus dt is nothing but Vc0 plus, and Vc0 plus is equal to 0. Also we know I0 plus is 0. So, substituting the values of R, L, I0 plus and V, we get di by dt 0 plus is equal to 10 ampere per second. Don't you feel that it is so simple? Now, to find d squared I by dt square 0 plus, let us differentiate equation 1. We get R into di by dt plus L into d squared I by dt square plus I by C is equal to 0. Let it be equation 1.1. This equation again is a general equation which holds good for all time t. So, it holds good for t is equal to 0 plus also. Hence, by adding t is equal to 0 plus in all the terms and substituting the values of R, di by dt 0 plus, L and I0 plus, we get d squared I by dt square 0 plus is equal to minus 100 amperes per second square. Hope you will enjoy solving such problems. Friends, let us consider another interesting problem in which we use yet another technique. In this problem, we are required to find the node voltage VA0 minus and VA0 plus. It is given that the circuit is in steady state when switch K is open. The switch K is closed at t is equal to 0. No initial conditions are given. We have to find them. If you observe the given network, there is only one energy storing element, that is inductance. So, we have to find IL0 minus. Therefore, let us draw the equivalent circuit at t is equal to 0 minus. We know that at t is equal to 0 minus, the switch K is open and the inductance will be short because it will behave as though it is at t is equal to infinity. So, first you should identify that the current through this resistance of 20 ohm is 0 as K is open. Hence, the circuit reduces to a two-loop network. By writing the loop equation for 1, we get 60I1 minus 40I2 is equal to 0. Let it be equation 1. Similarly, for loop 2 we get minus 40 I1 plus 60 I2 is equal to 100. Let it be equation 2. By solving these two simultaneous equations 1 and 2, we get I1 is equal to 2 amperes and I2 is equal to 3 amperes. Therefore, IL0 minus is equal to 3 amperes. So, IL0 plus also is equal to 3 amperes. To find VA0 minus, current in the branch AB is equal to I2 minus I1, which will give us 1 ampere. Hence, VA0 minus is equal to simple 20 into 1, which will give us 20 volts. To obtain VA0 plus, let us draw the equivalent circuit at t is equal to 0 plus. At t is equal to 0 plus, the switch K is closed and the inductance will behave as a current source of 3 amperes as shown in figure. You note that. Now, to find VA0 plus, let us write the nodal equations. For node VA, we get VA divided by 20 plus VA minus VB divided by 20 plus VA minus VC divided by 20 is equal to 0. By simplifying it, we get 3VA minus VB minus VC is equal to 0. Let it be equation 1. Similarly, for node VB, we get VB minus 100 divided by 20 plus VB minus VA by 20 plus VB minus VC by 20 is equal to 0. By simplifying it, we get minus VA plus 3VB minus VC is equal to 0. Let it be equation 2. Similarly, for node VC, we get VC minus VA by 20 plus VC minus VB by 20 plus 3 is equal to 0. By simplifying it, we get minus VA minus VB plus 2 VC is equal to minus 60. Let it be equation 3. By solving these three simultaneous equations 1, 2 and 3, we get VA0 plus is equal to 7.5 volts. Friends, you see that we have used different technique to solve this problem. Friends, we shall take up yet another interesting problem to find I di by dt and d square di by dt square at t is equal to 0 plus. It is given that the switch K is moved from position A to position B at a time t is equal to 0. You find that no initial conditions are given, hence we have to find IL0 minus and VC0 minus. So, let us draw the equivalent circuit at t is equal to 0 minus as shown in figure. We see that switch K is in position A and it is in position A for a long time or for an infinite time before changeover. So, circuit elements will behave as though time t is equal to infinity. Hence, at t is equal to 0 minus, L is short and C is open as shown in figure. From the equivalent circuit, we find that I of 0 minus is equal to 0 and Vc0 minus is equal to 40 volts. Note that positive and negative terminals of the source of 40 volts are connected to the two terminals of the capacitor. Hence, the capacitor is charged to 40 volts. Also note that current through 20 ohm resistance is 0 as C is open and current through inductance also is 0 as the branch is open. If we draw the equivalent circuit at t is equal to 0 plus, we see that K is in position B, L is open and C will behave as a source of 40 volts as shown. Therefore, I0 plus is equal to 0 and Vc0 plus is equal to 40 volts and we see that IL0 plus also is equal to 0. To find diabetes 0 plus, let us draw the circuit for t greater than or equal to 0 as shown in figure. The switch K is at position B. Also note that Vc0 plus is equal to 40 volts with the polarity shown. Hence, the system equation for t greater than or equal to 0 can be written as R into I plus L into di by dt plus 1 upon C into integration I dt is equal to 0. Note the applied voltage is 0, but there is initial voltage across the capacitor of 40 volts acting in the polarity shown.
Substituting the values of
1 upon C into integration I dt is equal to Vc, we get equation 2. You see that equation 2 is a general equation which holds good for all time t, so it also holds good for time t is equal to 0 plus. So, adding t is equal to 0 plus in all the terms, we get equation 2.1. By solving it, we get di by dt 0 plus is equal to minus 20 amperes per second. To find d squared I by dt square at t is equal to 0 plus, let us use equation 1.1. By differentiating it with respect to t and solving for d squared I by dt square at t is equal to 0 plus, we get d squared I by dt square 0 plus is equal to 200 amperes per second square. Friends, in the process of acquiring different skills, let us solve yet another interesting problem to find I1 of t, I2 of t and di1 by dt at t is equal to 0 plus in the circuit shown in figure. It is given that the steady state is reached when the switch K is open. So, it can be considered to be open for infinite time before closing. So, the switch K is open at t is equal to 0 minus also. Hence, the circuit elements will behave as though they are at t is equal to infinity. Hence, at t is equal to 0 minus, K is open, L is short and C is open. Therefore, we get the equivalent circuit at t is equal to 0 minus as shown in figure. From the equivalent circuit, we find that I2 0 minus is equal to 0 as C is open. Note that since I2 0 minus is equal to 0, no current will flow through this 20 ohm resistance. Therefore, you find that Vc 0 minus is the voltage across the branch AB. Friends, such thinking from your mind should reflect immediately. To find I1 0 minus, let us look at the closed loop from which we find that I1 0 minus is equal to 100 divided by 10 plus 20, which will give us 10 divided by 3 amperes. To find Vc 0 minus, let us write the Kirchhoff's voltage equation for the branch AB. We find that VAB is equal to 20 into IL0 minus, which will give us 200 divided by 3 volts. We know that inductance will oppose the change in current through it and capacitance opposes the change in voltage across it. Hence, IL0 plus is equal to 10 by 3 amperes and Vc0 plus is equal to 200 by 3 volts. Incorporating these aspects, the equivalent circuit at t is equal to 0 plus is drawn as shown in figure. At t is equal to 0 plus, the switch K is closed, so 10 ohm resistance is short circuited. Note that this is another important technique. It should strike immediately. Inductance is replaced by a current source of 10 by 3 amperes and the capacitance is replaced by a voltage source of 200 by 3 volts. You also note that there are two parallel branches, one in which I1 0 plus is flowing and another in which I2 0 plus is flowing. Very important point to note that source of 100 volts is applied across these two parallel branches. In parallel branch 1, there is a current source of 10 by 3 amperes present, hence I1 0 plus is equal to 10 by 3 amperes. To get I2 0 plus, let us write the branch 2 equation from which we get IT 0 plus is equal to 100 minus Vc 0 plus divided by 20, which will give us 5 by 3 amperes. To find di1 by dt 0 plus, consider the simplified circuit diagram shown in figure. By writing Kirchhoff's voltage equation for the loop, we get 20 I1 plus L into di1 by dt is equal to 100. This equation is a general equation which holds good for all time t. So, it should also hold good for t is equal to 0 plus. Hence, adding t is equal to 0 plus in all the terms and solving it, we get di1 by dt 0 plus is equal to 50 divided by 3 amperes per second. Hope you enjoy solving such problems. Friends, finally, let us solve a very simple problem to find I of t and di by dt at time t is equal to 0 plus, and also we have to find the complete solution for I of t for t greater than or equal to 0 using classical approach. Note that in the problem statement it is given that the initial current through the inductance as 0. Hence, straight away we can proceed to draw the equivalent circuit at t is equal to 0 plus. We see that at t is equal to 0 plus, switch K is closed and L is open. From the equivalent circuit, we find that I0 plus is equal to 0. To find the di by dt 0 plus, let us draw the circuit for t greater than or equal to 0 as shown in figure. Switch K is closed. Hence, the system equation can be written as 10 into I plus 1 into di by dt is equal to 100. Let it be equation 1. This equation is a general equation which holds good for all time t, so it also holds good for t is equal to 0 plus. Hence, by adding t is equal to 0 plus in all the terms and solving it by substituting I of 0 plus is equal to 0, we get di by dt 0 plus is equal to 100 ampere per second. To find the expression for I of t for t greater than or equal to 0 using classical approach, we have to obtain the system equation in the standard form of ODE. Hence, by rearranging equation 1, we get equation 1.2. By comparing it with the standard form of ODE, we get P is equal to 10 and Q is equal to 100. We know that the solution for I of t for a first order differential equation is I of t is equal to e to the power of minus pt into integration q into e to the power of pt dt plus k into e to the power of minus pt, where k is the integration constant. By substituting the values of p and q and solving the integration term, we get I of t is equal to 10 plus k into e to the power of minus 10t. We know I of 0 is equal to 0 at time t is equal to 0. Hence, by substituting in the equation of I of t, we get k is equal to minus 10. Therefore, by substituting k is equal to minus 10 in the equation of it, we get the complete solution of I of t, which is equal to 10 into bracket 1 minus e to the power of minus 10t amperes. Friends, evaluation of initial and final conditions of any given network is very easy and interesting if you are comfortable in basic concepts and little of mathematical knowledge. You also have to acquire the skills of identifying the changes in the connectivity of network elements after you draw the equivalent circuits. Regarding the behavior of inductance and capacitance, I suggest you remember and recall only one statement, that is, when inductance is switched across a step input at t is equal to 0, at t is equal to 0 plus, inductance is open. That's all. If you remember only this, you can extrapolate that at t is equal to infinity, L is short, at t is equal to 0 plus, C is short, and at t is equal to infinity, C is open. It is the reverse of inductance. Also, if there is initial current through the inductance and initial voltage across the capacitance, inductance will act as a current source and capacitance will act as a voltage source, both at t is equal to 0 plus and at t is equal to infinity. It is that simple. Friends, I have tried to make the explanation as simple as possible. Hope you have understood clearly the concepts explained. I am sure this tutorial has kindled some of your thoughts. If so, please forward your feedback and suggestions to my email. Thank you for watching this video.